Let's get started. Today we have Gary Harris from Howard University. Like I was saying, he's in several positions, and he has the enviable situation of actually being his own boss, which is something I admire, and it leads to quick decisions in certain critical issues. He's really done a great job there, both with their materials growth facilities and microengineering. And they have a wonderful new building that's put together on Georgia Avenue that integrates a lot of those things. It's really quite good. He's been active in the growth of diamond through different techniques. They have a couple new systems there. One of them I sort of admire but don't want to be too close to, which actually is both high temperature and high pressure, so that if it blows up, you really get walloped in a major way. I think, what is it, 2,500 degrees and 2,500 psi at the same time or something like that. Bought from Russia too, which means it must be good. So, but thanks, Gary. He'll be telling us today about these.
Okay. First of all, I'd like to thank you guys for inviting me, and I hope to give a sort of like an overview of or state of the technology as far as the growth of the materials concerned, in particular epitaxial layers and some things that we've been doing to enhance the performance of materials, of diamond in particular. I also wanted to share with you, did I talk loud enough?
Maybe.
Okay. I also wanted to share with you that this is a kind of a special time in the history of Howard. 2 weeks ago, we celebrated our 150th anniversary. So the sesquicentennial anniversary of the university took place on March 2nd. So it was a big to-do in Washington. We had a big Charter Day dinner, and we also, the new African American Museum, 2 of our alums, the director of the museum is a Howard alum, and so he opened the museum after hours, and it was quite an affair. So my plan of attack today is, first I just wanted to say a little bit about Howard, and then talk about diamond as primarily as a semiconductor material, epitaxial growth, some doping results, and then some of the applications that we like to employ that are somewhat different than some of the things that have been that we've heard so far. Just to again give you a little bit of facts about the university. This is our original seal of the university, and it's always been a place where education and knowledge for all. Howard started in 1867, the College of Engineering in 1911. The graduate school officially, although we offered graduate degrees, the graduate school as an entity actually started in 1958. We have 29 programs, 18 of them in the STEMS area. We have over 1,000 students. We have 20 PhD areas. The largest undergraduate program is in biology. We have over 1,000 biology majors at Howard. And the Chronicle of Higher Education, their most recent report, which goes back to 2008, 2012, says Howard produced the largest number of undergraduates to go on to get their PhDs, which was 339 African Americans. We graduated the first female to get a law degree, both black or white, in America in the early 1800s, right after the founding of the university. I believe it was 1872. And we have about $60 million of sponsored programs to date. We've graduated over 100,000 undergraduates and 10,000 master's students and over 3,200 PhDs. So that's just to give you a little idea of the scope and breadth of the university. Today I want to talk about diamond and really when you talk about diamond, there's one really important person that many of you may have not heard of that was really involved in the initiation of diamond in the United States. His name was Max Yoder, and Max Yoder worked for the Office of Naval Research, and it was Max Yoder who went over to Japan and spent time in Japan and brought back the essence of why diamond was an important material. He also emphasized silicon carbide, and that was his mission in life. He would be really proud to see all the kinds of activities that have been going on in diamond in recent years. And in the beginning of that mission, he was a lone wolf. He was the only one touting diamond as a interesting material for lots of different applications that we've been able to realize today. So I always like to just say a few words about Max Yoder. Well, you probably seen this chart a few times. These are just some of the various semiconductor parameters and properties compared to each other. We have diamond, silicon, of course, is what I call the Volkswagen of the semiconductor field. Gallium arsenide and silicon carbide, and this really represents the 6H version of silicon carbide, although silicon carbide has over 100 different polytypes. There's a couple of things that are just really interesting that jump out at the chart. One is the hardness of diamond, and in fact, just recently when Apple wanted to develop their new watch, they had actually considered making the face out of diamond because they wanted a scratchless watch. And they eventually settled on aluminum oxide because it was one of the second hardest materials that they could do and make. There's also some really interesting electrical properties about the material, and its thermal conductivity is one of the highest that we know about of any material. And it's a simple structure. It just involves, it's an elemental compound, as we well know. But one of the things that's really interesting to point out is that its lattice constant is very, very small. And that presents certain problems of trying to match or to grow materials on heteroepitaxial materials on top of diamond without a lot of strain in it, because it has this very low lattice constant. There's some other things that are really exciting. Its dielectric constant is low, and of course the index of refraction of the material is low, and it has a wide band gap, which means that there's a lot of room in the band gap to do all kinds of different band gap engineering ideas and dopants that people have been taking advantage of for quite some time. I just wanted to also bring you up to date, if you probably haven't seen this in a while. This is the band structure of diamond compared to that of silicon, and this is the cubic version of silicon carbide and gallium arsenide. Of course, it's an indirect band gap material, which means that the minimum of the valence band and the maximum of the conduction band do not line up at the origin here, or the gamma point. They're off. And so this usually means that if we're going to think about using this material as a laser, it might present some problems. But it may also be easily used probably as an LED device. And if you look through all the literature, you'll see that most direct band gap materials, many of them have lasing capabilities, because it's a single photon process as opposed to a photon and a phonon that have to be involved in the transfer of energy from the conduction band to the valence band, or vice versa. So people have developed a number of applications from taking advantage of its mechanical properties, like speakers and windows. Just recently, a lot of people started to do some electrical take advantage of its electrical properties. Again, with more mechanical properties. There's some medical applications, of course, the spin electronic applications. And then something that we've been working on a little bit is on the superconducting properties of diamond. Diamond is a superconductor, a type 1 superconductor, if it is heavily doped. So let me just give you a little bit about the history of the material. The first group to synthesize synthetic diamond was in 1955. That was done at General Electric. And they developed what they call the high pressure, high temperature process, which is really the genesis of all the bulk material that's being grown today. In 1993, I went over to Russia to visit this group right here that did some of the continuous growth using hydrogen methane. I went over to visit them, not to get a contract or anything like that, but to they were also involved in silicon carbide work. And so I was our group at Howard was involved in some of the early silicon carbide work that was done here in the U.S. Later on, a few years later, 1982, a CVD process was developed. And of course, today, we have at least one company, and there are a couple of other small companies that also do bulk growth of diamond. Element 6 is probably the largest producer of bulk material. So most of the exciting things associated with semiconductors take place in the epitaxial layers, and there are two predominantly ways of growing epitaxial silicon carbide. The first one is called the microwave enhanced plasma growth, where you actually produce a microwave plasma, and that microwave plasma creates the free radicals that help initiate the growth of diamond. And the other technique is called the hot filament growth technique, where you actually pass the gas over a super hot filament, and that hot filament creates the free radicals that are involved in the actual growth process. There's some advantages and disadvantages of both of these techniques. I'll try to point some of those out as I go through our discussion today. And of course, let me just also remind you that diamond is somewhat related to graphene. It's only, they're all both carbon atoms, but the difference is, of course, in the hybridization and the bonding where you have sp3 bonds as opposed to sp2 bonds, and sp2 bonds are those associated with graphene. So the process is pretty simple of how we do the chemical vapor deposition process. Is we have to create these free radicals, and these free radicals then impinge on the surface and if there are a number of nucleation sites, and I'll tell you a way in which we can enhance the nucleation. There's of course a chemical reaction, and we can get the formation of diamond. And there's some things that you can add to the reaction that help facilitate the growth of diamond versus graphene or carbon-based compounds. So this is a very similar chemistry here for both the microwave enhanced plasma growth technique and also the hot filament technique. So one major issue is substrate technology. Right now, even with the major advances that Element 6 have made in the last few years, their substrates are relatively small in size. They're still about 5 to 6 millimeters on a side, and somewhat expensive. So when the graduate students drop them or the faculty member drops them, everybody's looking on the floor to try and find it because it represents a lot of value, and since it's clear, it's even more difficult to find. So you see people on the ground leaning and doing all kinds of things to figure out where their sample is. But we would like to grow heteroepitaxy, if we could, materials on top of other substrates that are more readily available just from a production perspective. If some of the things that we plan on doing with diamond are ever to go into the production mode, this is one problem that we got to solve. We have to have a large area substrate for commercial applications. So we've looked at a lot of different things or ways to try and see if we can grow a large area diamond on, or high quality large area diamond on a heterostructure kind of arrangement, heteroepitaxy. So here are some of the things that we considered. We considered little or no solubility or reaction with the diamond, carbon dissolving and weak carbide formation, strong carbide formation. So we looked at a whole bunch of different substrates, not only their chemical makeup, but their crystalline structure as well, to see if we could mix and match some of those substrates so that we might have a chance of epitaxially growing high quality diamond on some foreign substrates. And there's some real advantages to that because, first of all, silicon technology is pretty mature. We can even, to this day, we can grow 12-inch silicon wafers. Silicon carbide, another candidate. Right now, the state-of-the-art is about a 6-inch wafer. So if we could use that technology, then we would begin to take this from an experimental perspective in the laboratory to maybe a slightly low-cost production or production kind of technique. So they're cheaper. These substrates are cheaper than diamond. Can we grow large area substrates? As we mentioned before, the biggest piece of diamond substrate that I've been able to identify is about 10 millimeters by 10 millimeters, and it costs about $4,000. Easily, you can get silicon carbide and other substrates that are greater than 200 nanometers for about half of that price or even less. Silicon carbide has a similar structure to some of the properties of diamond and graphene, and so there might be some synergy of not only taking advantage of growing diamond on top of silicon carbide, but you might also get graphene as another byproduct of that substrate technology. So the useful silicon carbide properties would include large band gap, large thermal conductivity, low coefficient of thermal expansion, is chemical inert. And this is a real big advantage if you want to think about diamond as somewhat of an electronic device. The fact that you can get silicon carbide semi-insulating substrates. So that's really a big issue. And it's one of the main reasons why people have done sublimation of graphene on silicon carbide is because now they have a semi-insulating substrate technology. And also silicon carbide comes in lots of different polytypes. There's over 150 crystalline structures of silicon carbide that we know about, although 3C, 6H, and 4H are the predominant ones, along with those are the predominant ones, but there are other ones that include 15R and 2H and all kinds of different combinations of crystalline structures that can form based on the basis of growth. Some of these may not be thermodynamically stable, but they may offer some possibility for growth on a foreign substrate. So I like to call silicon carbide a cousin material to diamond, and this is one of the manufacturers of large area silicon carbide. That's Cree Research. Several of my students were involved in the forming of this company, as well as the folks at North Carolina North Carolina State University, Robert Davis's group. And the interesting thing is when my students left, they would never tell me what they were doing, and they were really secret about all the kinds of things that they've done related to their substrate technology. But Cree is a viable company now. They has started out just making silicon carbide wafers and silicon carbide technology. They have spun that off into first putting gallium nitride on silicon carbide for LED applications, and now they also grow various kinds of substrates, and they're probably the largest producer of gallium nitride white LEDs in the U.S. certainly. So we set out to try and see if we could grow this silicon carbide, and we connected with a local manufacturer. It's called Blue Wave Semiconductor, and we helped design this first version of our reactor. We tried to include a lot of different features in it to make it as flexible as possible. First of all, it's a high vacuum chamber. It goes down to 10 to the minus 8. We have mass flow controllers on it that control a variety of the gases that are involved in the reaction. We use hot filaments. We use tungsten wires, and we pass a tremendous amount of current through those tungsten wires, and the temperature of those tungsten wires are typically around 2,500 degrees C. That the gas passes over to create these free radicals. The substrate temperature is typically as high as 850 degrees C. Our first version involved a 1-inch, but now we have actually a 2-inch substrate stage. And we also have a rotating substrate, so to help with uniformity. And we also have a second stage that's in this particular reactor that goes to 1,000 degrees C. It's a non-rotating stage, and we were thinking about using it for some conventional CVD inside the same reactor. One thing that's very, very important is the spacing between the filaments and the actual platform where the wafer sits, a susceptor. And so we can adjust that. That's the Z stage, so we can adjust the height. We've also added some diagnostics to give us some idea of what's taking place inside the reactor as we grow. One thing we added, one of the earliest things that we added was a laser interferometer attachment, so we can actually measure in situ the thickness of the layer as we grow it. And then recently we've started out with some optical emission spectroscopy, and we can bias the substrate relative to the filaments, and we can actually create a plasma as well as the hot filament effect, and we call that plasma enhanced nucleation, and that can speed up the growth rate as high as 10 microns an hour. Typically, without the biasing, we're about a quarter to a half of micron an hour, somewhere in that neighborhood, depending on the gas flow. So it's capable of uniform. One of the big advantages of the hot filament is it's a scalable up technology. We have on the drawing boards already a 4-inch, and I'll show you an example of a 4-inch hot filament CVD system for growing diamond. So it's easily can be scaled up. Much easier to scale up than compared to a microwave plasma system. We can do low pressure deposition. It's really easy to operate. The students can learn how to operate it pretty quickly. It can do both polycrystalline and single crystal materials. And we've added a lot of doping. So nitrogen doping, the in situ growth measurements, and of course the gas species study, which we can use an optical emission spectroscopy to do. So those are some of the things that we have added, and this is sort of our argument why we have invested in the hot filament versus the microwave plasma approach. So how do we grow heteroepitaxial material on top of a diamond on top of a foreign substrate? So what you have to do is you have to create a lot of nucleation sites for the micro diamond or nano diamond to initiate its growth. So one way that we do that, and there are lots of ways to do that, is we use a diamond slurry that we actually spin on to the surface of the material. It leaves behind these nanoparticles of diamond, and then they act as nucleation sites and for the growth of diamond, and that coalesces into a continuous film. We also have to control the concentration of the gases so that we can grow diamond versus graphitic material. So there's a competition between diamond and a graphitic material that can grow, and by adding certain gases like argon, you can force the reaction to go in the favor of diamond versus graphitic, and I'll show you how we can prove that that's the case. So I just put this on here. This is the laser interferometer. Basically, we point it at the surface, and of course you get destructive and constructive interference. If you know the wavelength of the laser, you can, and the index of refraction of the material, you can actually in situ measure the thickness of the layer, and this is each one of these layers as they're growing, actually doing the actual growth process. We've also, we can also add a bias. This is with zero volt difference between the filaments and the stage. This is with 200 volts difference, and you can see that you've ignited a plasma, and we can actually use that plasma to study some of the gas dynamics that are going on. Also, the plasma actually, the bias actually enhances the nucleation. You get highly oriented growth in the 1-1-1 direction. The growth rate can go as high as 10 microns an hour, and it produces somewhere around 10 to the 11th square centimeter nucleation sites. And with this bias, by taking a spectrum of the colors of the gas that are created in here and subtracting off the background, you can actually identify the various peaks that are associated with various free radicals that you can monitor during the growth process. So the first thing that we did is we tried to calibrate the quality of our system. So we took some high quality bulk grown diamond, and we grew epitaxial films on it. And one of the easiest kind of straightforward experiments that you can do is you can measure the full width of half max of this peak, which is indicative of the quality of the diamond. Elemental diamond Pure diamond has just this one Raman peak here, and the full width at half max tells you about the quality of the crystal structure. So this is the bulk material plotted on top of the epitaxial material. You see a little peak out here. This kind of represents some graphitic component to the substrate, a very low percentage. You see that the full width at half max for both the as-grown and the bulk substrate are pretty much almost identical to each other. This is an example of what the surface looks like after growth on single crystal diamond. This is the surface after we've grown on silicon, 6H silicon carbide, N-type 6H silicon carbide, 3C type silicon carbide, and this is various stages during the growth. This one being more advanced, these two being more advanced, and this one was stopped deliberately so we could get some idea of how the nucleation takes place and how the coalescence of, how the substrate the epitaxial film actually comes together as a result of the growth process. We also have studied the interface. One of the things that we were really interested in is seeing what kind of interfaces we can make. This is with silicon, and this is silicon carbide. With the silicon, we get a very, very sharp interface between the diamond and the silicon. However, with silicon carbide, we get this gradual sort of interface, and that's primarily due to some graphitic compound that seems to build up at the interface of the diamond. This is diamond up here, and this is the silicon carbide. These are some Raman measurements of on foreign substrates. So this is on a silicon substrate, and this background here is just the diamond to give you an idea of this little additional peak here, this graphitic peak here that's present in the epitaxial growth of silicon on epitaxial growth of diamond on silicon. The full width at half max is not quite the same as that of a high quality diamond film. So one of the things that we want to do is we want to take advantage of all the color centers associated with diamond. And of course, you are familiar with those. In fact, the reason why the Hope diamond, which is one of the biggest diamonds in the world, is purple is because it has boron in it. It has boron as an impurity. And all these different impurities produce various color centers inside the diamond and allow it to fluoresce at these different colors. So if we want to make useful materials out of semiconductors, it's always the impurities that are important and controlling those impurities. So we have began to work out all the several different types of impurities that you can put in a diamond. If you're interested in probably more electronic properties of diamond and using it more or less as a traditional electronic device, you need substitutional impurities. So you need boron and phosphorus. Of course, boron makes it p-type, phosphorus makes it n-type. These are the activation energies associated with that. And you'll notice that instead of being a few MeV, which is the case for silicon, these are about a half or so of MeV, which means that they're not 100% ionized at room temperature. You can also put in nitrogen, and of course we already know something about nitrogen that allows us to do some qubits kinds of stuff and also magnetic sensing. But you can put in silicon, which creates a single photon source, and germanium, which is very similar, another single photon source. And we also been fooling around with other substitutional impurities. like sulfur. And then there's also some things that you can do at the surface to terminate the surface and make it either P-type or somewhat P-type or N-type, depending on how you terminate the actual growth itself. So if we want to put some of these impurities in there, how can we begin to put those impurities in there? Well, we have gaseous sources, we have some solid sources, and then one thing that we've developed a new fusion cell, where we actually, these are cells that are typically used for MBE growth. And the reason why is because, number one of the biggest, one of the best N-type dopants is phosphorus, and the source of phosphorus is phosphine, which is, of course, pretty toxic material, and so we don't want any of our students handling that. So we have been developing a gallium phosphorus a fuse cell. We also can use solid sources. The problem with the phosphorus solid source is it tends to stay around for a long time. We can also use gaseous sources like diborane for boron, and also germane and silane for silicon carbide. And people have also done ion implantation. And the key there is that you do hot ion implantation. You do it into a hot substrate where the substrate is at about 500 degrees C, so that you get some recovery even at during the implantation process. One of the big interesting, of course, centers is the NV center, and that's the artificial atom, a single electron spin system that can easily be read out optically. Most of you already know a whole lot about that. But one thing that we've been working with is also, instead of using silicon, instead of using nitrogen, we can replace the nitrogen with a silicon. And what happens with the silicon is that it creates a symmetric two vacancies on both sides, and that sort of cancels out the phonon response for this and produces a single electron type level, single photon electron type level. And you'll see that when we show you some of the photoluminescence data. The same thing here occurs for germanium, and the wavelengths associated with these are slightly different. So if you want to talk about deep color centers, you have the NV center, you have the silicon vacancy center, and you have the germanium vacancy center. Here's just some data that we've been able to accumulate, where the zero phonon line is for the NV center, well known for silicon and for germanium. Full width at half max. If you notice, the NV center is very broad. However, the silicon and germanium are very, very sharp. There's the phonon coupling is very strong in the case of the NV center, very, very weak in the case of silicon and germanium. It appears that the nitrogen vacancy is more of a candidate for room temperature as well as cryogenic temperatures, but qubit kind of memory, whereas the silicon and germanium are more apt for single photon sources at these two respective wavelengths. The full width at half max is very, very sharp, 3 nanometers. So how do we put traditional boron in? We've used a boron oxide, and this is an actual picture of our little container of the boron oxide as we actually grow the sample. And these are the growth parameters. And This is some SIMS data from of typical growth under certain kinds of pressured conditions of the gas flows. So you see right here, this is the background. That's just the carbon signal. So we normally take that to make sure that there's no strange things going on with the SIMS data. So that should be uniform throughout the whole sample, and it is. And then what we done is we turned on different pressures of gases of the methane during the growth process. And you can see how we can kind of vary the incorporation. I wouldn't pay too much attention to the actual magnitude of the concentration, since this is done, this is SIMS work, and it's very hard to accurately quantify the carrier concentration using this technique. We also have done Auger on the boron doped material, and as you begin to add boron to the sample, what it has, this is your baseline high purity diamond. As you add more and more boron, the Raman signal gets distorted like this here. So this is our sample here. This is some stuff that we found in the literature, and it sort of verifies that we, in fact, another way of verifying that you have boron into the diamond. And you can just physically look at the diamond films. They're blue. So, and I don't know if you can see it right here, but there's a slight blue tint to it right here. This is some actual Hall measurements that we've made on some of the boron blue, as we call it, substrates. And this is the mobility and the carrier concentration. We don't, with this solid source technique, we don't have a whole lot of variation in the doping concentration because it's hard to determine set the vapor pressure of the boron. Of course, this is a famous nitrogen vacancy center here. I'll just quickly go over that, skip that. What we want to do is, if we want to use nitrogen for some of our applications, we have to develop what we call delta doping. That is, to be able to put a thin plane of nitrogen atoms, NV centers, near the surface, or be able to bury them inside the surface by a certain, at a certain distance away from the surface. So what we've done is we've experimented with delta doping. That is, basically we put a plane of nitrogen atoms, or we turn on the nitrogen source for a short period of time during the growth, and that produces almost like a spike impulse delta response in the nitrogen concentration, and then we take a look at the actual profile. So, and the way we did that is, one of the problems that we were worried about is nitrogen 14 and silicon doubly ionized have the same atomic charge to mass ratio. So we put in nitrogen 15, and we've been able to change the doping over a fairly wide range by just changing the concentration of the nitrogen in the material. So this is a single layer that we grew, and these are all the different pressures that we grew it at, flow rates of the nitrogen 15. And when you buy nitrogen 15, the nitrogen 15 is not as pure as you might think it is. It has about 5 to 10% of nitrogen 14 in it. But we wanted to make sure that that it was tracking according to our gas concentrations, and we were looking at nitrogen as opposed to looking at silicon And we wanted to just make sure there was no out diffusion from the substrate in the case of silicon carbide or silicon. We've also put a spike near the surface, so slow down the growth rate, and about a 12-minute growth that produces about 3.2 nanometers thin, thick layer of nitrogen near the surface, and then we do and see how that nitrogen has been spread out as a result of that. And if you calculate the bi length, you'll see that for this material, the bi length is pretty wide. And so when you try to put a very, very super thin layer of nitrogen in, it does spread out a little bit. Oh, I'll skip this. That just talks about the NV center. And this is just some of the growth parameters. We've done these super thin layers in silicon carbide, and at the surface, slightly below the surface, all different kinds of possibilities. Here's the actual fluorescence of the NV center of diamond on top of, that we grown on top of diamond. And Marco told me this was one of the strongest NV centers that they've observed. And it might be because we primarily put it near the surface of the wafer. We've also done fluorescence on the silicon NV center as well. This is the silicon NV center, and you notice how sharp it is. And because of the phonon coupling, weak phonon coupling, you don't have the side bands that you had when you had the NV center. And we've also been able to isolate a single silicon vacancy, and you can see we do a scan across the entire wafer, we can identify a single silicon vacancy. And we put all of these sort of together, the silicon, the nitrogen vacancy, and also the germanium vacancy, all together here. And the different colors. The blue is the, I believe that's the nitrogen vacancy. That is the silicon vacancy, and where's the other one? There's the germanium one. So those are the three luminescence signals associated with those vacancies. So there they are, 602, that's the nitrogen zero phonon line, and that's the silicon zero phonon line. And these are the gas rates that we, for this particular sample, the relationship between the impurity and the methane concentration. We've also been exploring with ways in which we could make pillars. Marco has developed a great way using reactive ion etching and e-beam lithography. We wanted to see if we can make some of these pillars using diblock copolymers. So we have a recipe for these diblock copolymers, and the size of the diblock copolymers depend on the molecular weight of these materials. So the process is sort of like this. You start out with a diamond substrate, you spin coat the diblock copolymer on it. You activate the diblock copolymer, typically either with a UV light or temperature, and then you do reactive ion etching, and then you're sort of left with the diamond pillars. So these are some samples after we've done the reactive ion etching of them. One of the things too that we've also explored is boron doping in diamond, and the reason why is because these mechanisms right here, as the concentration of the boron increases in the diamond, the substitutional nature goes to a hopping mechanism, and then eventually the conduction mechanism is more metallic. And so near this, in this region here, this is the region in which we've observed that the boron, heavily doped boron, turns into a type 1 superconductor. And that's because you get the slowdown of the molecular vibration, so that you have to take it down to a low temperature, and the electrons team up in the Cooper pairs, and you get what people like to call perfect diamagnetism. And just to show you that we've been able to do that in some of our samples, and this is the resistance here versus temperature. These transition temperatures are around 3 to 2.7, depending on where we are on the surface of the sample and the nature of the doping of the boron. One of the things that we've also done is we've tried to take advantage of some of the mechanical properties of the diamond film, and it turns out that this is the neutron source at Oak Ridge National Lab in Tennessee. And one of the most important things of this, you would think that of this whole neutron source, is the ability to create neutrons, and it all depends on this hydrogen stripping technique, where they accelerate a beam of a hydrogen beam into a thin film of diamond, and there's an actual reaction that takes place, a collision, and then out comes the neutron. So that thin film has to be able to withstand huge amounts of heat, and diamond is one of the few materials that has the thermal conductivity to do that. So the thermal conductivity, you have to also have a low molecular weight. The foil has to be very thin, and the foil should change very little depending on the source of protons that hits the source. So we developed a process of making thin film nano diamond on silicon, and we use molybdenum on the backside. We thin it down, we anneal it to remove some of the stress, and we can make thin films, transparent thin films of 1 micron or less of diamond on top of silicon substrates. So this is the granddaddy of our new reactors. It's a dual chamber system where we can load lock, bring in a wafer, put it in either the P chamber or the N chamber, all in the same growth process, and it has a 4-inch wafer capability. We hopefully will be getting this sometime this summer and have this operational very soon. So there's a lot of future activities that we're working on. If we can ever clearly identify how to make N and P material, we'd like to make UV LEDs and UV detectors out of diamond. There's a tremendous market for a UV LED. Tomorrow you'll hear from Aaron Jackson, one of our postdocs, who's developed a technique for making quantum registers, and by incorporating nitrogen and carbon 13 in a layer structure, and then putting a Schottky diode on top of that to modulate between the various NV centers. We've been studying the different phases of diamond growth mechanisms and depth, and how they can affect the quality of the diamond. Studies on the way to enhance, to get larger grain boundaries, and the way we're doing that is what we call the BEND. It's bias enhanced nucleation during the growth process. And then I like to thank the CECOM, NSF, for sponsoring us, our collaborators here at Harvard, MIT, and PGC. And if you get a chance and you want to hear about how great a relationship we have with Howard and MIT and PGC and our whole network, we did a TED Talk. So you can go to the TEDx and watch the TED Talk. So I leave it there, and I'm almost right on time. So I'll take questions for a short period, but if there are any questions.
Questions?
Yes.
What precision do you get on measuring the layer thickness with your interferometer?
Probably down to a tenth of a nanometer or something like that. Pretty accurate. We've checked it with a surface profilometer as well, where we've grown and etched the diamond away and got the step height and compared that to the step height that's predicted by the laser interferometer.
Good question.
Is there any way to control the distribution of the dopants to make them ordered somehow?
We think they're uniform,
Yes, but
Uh,
random, right?
but random. The other thing is that in some cases we put too much nitrogen in. So we want to kind of, that's one of the new missions that we got to do, is figure out what that concentration is so that they're not so clustered together, so that you have kind of like 1 MV per certain unit area or something like that. So we like to really do that. We also like to work on this whole question of the single photon source and using that for quantum keying applications.
I just wonder, for you growing the single crystal or diamond at the beginning using silicon, you have nanoparticles, then you grow. So should have transition period from nano or some defect level to single crystal. Is there anything like that? Or
Yeah,
you got single crystal.
no, we don't get we get large grain poly. That's what I would say.
Okay.
Not if we grow on a foreign substrate, we get large grain poly. There's some techniques that we've been trying to see if we can grow single crystal on top of a foreign substrate. So there are a lot of tricks. People have been very successful in the case of gallium arsenide and other systems where they've done all kinds of things, picked the right growth plane and all of those kinds of things, and you can get two dissimilar materials to grow on top of each other, and the material can be single crystal. We haven't found the sweet spot for silicon, for diamond yet.
Any other questions? Yeah.
So this kind of thin film stuff is pretty cool. These are polycrystalline thin films?
Yes. Mm-hmm.
How big are the grains?
The grains are, some grains are as large as 20 microns, and then some are even, sometimes we even get coalescing more than that.
And what is the thickness of the thing?
We've grown as much as
Foil.
the 35 microns. And with the enhanced plasma technique, the growth rate is much faster, so we're looking at growing these 10, 15 micron films in 1 hour, as opposed to 8, 9 hours. And the interface, the interesting thing is that once you grow these thicker layers, you can separate them from the silicon substrate. And the interface between...
Because of stress or
you just etch away or make the silicon substrate sacrificial and etch it away. And the interface is smoother than the top surface. So the interface between the silicon and the silicon carbide is shiny, very, very smooth. The average roughness is less than 100 nanometers, but on the surface it's even much more, like 250 nanometers, that kind of stuff.
Any last question? If not, let's thank Gary again. And of course, students need to sign up down.
Okay, thank you. I hope I tried to make it so that people understand more.
Clean plate of ignorance.
Mhm.
Enjoy the dinner.
Okay,